Swim bladders are known for helping fish control their buoyancy. However, there's also been research that suggests swim bladders are used to determine depth through hydrostatic pressure, helping them navigate vertically. Fish have the challenge of navigating and orientating themselves in 3 dimensions through space, and as you can imagine, this could be quite disorientating with no other environmental cues in the middle of the ocean. So how do they know up from down? Imagine yourself as a fish in the open water without any environmental objects nearby, just surrounded by blue water. So how are you going to navigate? How are you going to know for up from down, and which direction to go in, both vertically and horizontally? Fish are very cleverly adapted to this problem, as they are able to use their swim bladder to detect changes in pressure, and therefore can determine their depth using hydrostatic. As you can see in these diagrams, fish use the contraction and relaxation of their swim bladder to control their buoyancy. To float up, the swim bladder relaxes, increasing the volume of gas, and the opposite occurs to allow the fish to sink, with the muscle walls contracting and tightening. However, these fluctuations of gas were thought to prevent fish from detecting absolute depth, because the volume of gas varies with pressure, but also with the amount of gas it contains, therefore, in theory, preventing the use of hydrostatic pressure, because fish are constantly moving up and down through the water column. But research has shown that the inflation of the swim bladder does not necessarily overwhelm the fish's nervous system, and fish can regain sensitivity to pressure changes shortly after vertical movements, and therefore use hydrostatic pressure to determine their depth. So, what is hydrostatic pressure? It is the pressure that is exerted by a fluid at equilibrium at a given point within the fluid due to gravity, and increases in proportion to depth, measured from the surface because of the increasing weight of fluid, which exerts a downward force from above. If you look at this diagram, it shows a closed container filled with fluid. If big P is the hydrostatic pressure at the depth of h from the top surface of the fluid, the hydrostatic pressure at depth h is therefore due to the pressure exerted by the fluid above it. Here the equation shows you how the different forces act together. In a paper by Graham Taylor, he suggests that absolute depth could be estimated by fish during fast, steady vertical displacements. This is, he believes, done by combining a measurement of vertical speed with a measurement of the fractional rate of change of swim bladder volume. This works even if the amount of gas in the swim bladder varies for buoyancy. However, only if this variation occurs over a much longer time scale than changes in volume during displacement will it allow the telestone fish to sense absolute depth by using hydrostatic pressure cues. This use of hydrostatic pressure for navigation allows the fish to have a stable global reference for their vertical location that they can use constantly. And it means they do not have to rely on other navigational cues such as sound, physical landmarks, or chemical cues.